Feature engineering is the process of transforming raw data into meaningful predictive signals that can be better leveraged by machine learning models. By creating optimized data representations, feature engineering enhances model performance and predictive power. In this section, we'll explore essential tools and techniques for effective feature engineering to get the most out of your data. The main objective of feature engineering is to create new and transform existing features to enhance the performance of machine learning models. By developing innovative data representations, we can capture complex patterns and relationships in the data that may not be evident in the original features. Modifying current variables can also improve their predictive power and relevance to the model, leading to better overall performance. Ultimately, the goal is to boost the accuracy, efficiency, and interpretability of the machine learning models, making them more effective for the intended applications. The feature engineering process is a critical step in building effective machine learning models. It involves a series of iterative steps to prepare the data and create useful features. First, we need to deeply understand the problem we're trying to solve and the data we have available. Next, we handle any missing values in the data, which could impact model performance. We then encode any categorical features so the model can work with them. Scaling numerical features is also important to ensure they are on a similar range. Finally, we transform and extract new features from the data to provide the model with the most relevant information. Each of these steps builds upon the previous one, creating a robust foundation for the machine learning model. Feature transformation is the process of modifying, converting, or creating new features from existing data to improve model performance, data interpretability, and computational efficiency. It ensures that data aligns with the assumptions of machine learning algorithms. Feature transformation can improve model accuracy by aligning features with algorithm requirements, like scaling for distance-based models. It can also reduce redundancy by removing unnecessary or repetitive information from the data. The key benefits of feature transformation are improved model accuracy and reduced data redundancy. Feature transformation is a crucial step in machine learning as it helps address common data challenges. It can convert non-normal data into a normal distribution, which improves the validity of model assumptions. Dimensionality reduction techniques like PCA can simplify high-dimensional datasets, making them easier to work with. Feature transformation can also improve the interpretability of machine learning models by making feature relationships more understandable. Another key benefit is the ability to handle different data types, such as converting categorical variables into numerical formats suitable for ML models. Feature transformation is a critical step in machine learning to prepare data for modeling. We'll cover some common techniques used for feature transformation, including scaling, data transformation, and encoding methods. Scaling techniques like min-max scaling, feature scaling, and standardization help standardize feature values to a common range. Data transformation techniques like log transformation and handling textual features can help normalize distributions and work with different data types. Encoding methods like one-hot encoding, dummy encoding, and feature hashing allow us to work with categorical variables in machine learning models. Min-max scaling is a technique that rescales feature values to a fixed range, typically 0 to 1 or -1 to 1. It maintains the original distribution of the data but compresses it into the defined range. The procedure involves taking the original value, the minimum value in the dataset, and the maximum value in the dataset. This allows us to transform the original data into the target range while preserving the relative relationships between the values. Min-max scaling is commonly used in distance-based algorithms like KNN and K-means to ensure all features contribute equally to the model. Feature scaling, or normalization, is the process of adjusting the range of data to a specific scale, like 0, 1. This is useful when working with features that have varying scales or units to ensure they are on a common scale. The procedure involves calculating the minimum and maximum values, then linearly transforming the data to the desired range. For example, if the original feature values were 5, 10, 15, the normalized values would be 0, 0.5, 1. Normalization is important in computer vision tasks, where pixel values need to be scaled. It's also crucial for neural networks, which require normalized inputs to converge faster during training. Standardization, also known as variance scaling, is a technique that risk-scales data to have a mean of 0 and a standard deviation of 1. This ensures that all features have equal variance, which is important for many machine learning algorithms that assume normally distributed data, such as logistic regression, SVM, and PCA. The formula for standardization is x mu/sigma, where mu is the mean of the feature and sigma is the standard deviation. As an example, the original data 1, 2, 3 would be standardized to -1.22, 0, 1.22. The log transformation is a powerful technique that can help reduce the impact of extreme values and skewness in a dataset. It works by applying the logarithm function to the data, which compresses the range of the values and makes the distribution more normal. This can be especially useful for datasets that have a lot of variability, like income data, where there may be a few very high values that skew the overall distribution. By log transforming the data, we can make it more suitable for regression modeling and other statistical analyses that assume a normal distribution. Let's look at an example to see how this works in practice. The original data shows values ranging from 1 to 1,000, which is a very wide range. After log transformation, the values are much more compressed, ranging from 0 to 3. This log transformed data will be much more well-behaved and easier to work with in our analysis. Categorical data is information that can't be easily quantified, like colors, brands, or types of products. Encoding converts these categories into numerical values that machine learning models can understand. Label encoding assigns a unique number to each category, which works well for ordinal data, where the order matters, or when the order doesn't matter. One-hot encoding creates a separate column for each category, which is ideal for nominal data, where there's no inherent order. Ordinal encoding preserves the order of categories, making it suitable for ordinal data where the order is meaningful. These encoding techniques are especially useful for tree-based algorithms like decision trees and random forests. One-hot encoding is a technique used to represent categorical variables as binary columns. Each category is represented by a binary vector, where a 1 indicates the presence of that category and 0 indicates its absence. For example, if we have categories red, blue, and green, one-hot encoding would represent them as 1, 0, 0, 0, 1, 0, and 0, 0, 1 respectively. One-hot encoding is commonly used in linear regression and neural network models, as these models require numerical inputs. By converting categorical variables to binary columns, we can effectively incorporate them into these types of models. Dummy encoding is a technique similar to one-hot encoding, but it drops one of the categories to avoid the dummy variable trap. With 3 categories, red, blue, and green, dummy encoding would represent red as 1, 0, and blue as 0, 1, dropping the 3rd category. This helps prevent multicollinearity in regression models, where the variables are highly correlated with each other. Dummy encoding is a common preprocessing step for categorical variables in machine learning and statistical modeling. Feature hashing is a memory-efficient technique that maps high cardinality categorical features into fixed-size numerical vectors using hash functions. This helps reduce feature dimensionality while preserving the statistical relationships in the data. A key benefit is that it can handle new, unseen categories automatically in real-time systems. Feature hashing is widely used in natural language processing to convert large vocabularies into fixed-length vectors. It also powers recommendation systems by efficiently encoding user-item interactions. This technique enables real-time processing in memory-constrained environments. Feature hashing is particularly useful for click-through rate prediction, where new categories frequently emerge. Textual data is crucial for many machine learning applications, but it needs to be transformed into numerical representations that algorithms can understand. TF-IDF is a technique that measures the importance of words by looking at how often they appear in a document versus how unique they are across all documents. Word2Vec creates dense vector representations of words that capture semantic relationships and context between them. These textual feature extraction techniques power a wide range of natural language applications like sentiment analysis, spam detection, content categorization, and chatbot response generation. The key is transforming raw text into numerical formats that algorithms can leverage effectively. Missing values are common in data and can cause problems for machine learning models. Imputation is a common technique to handle missing values. Replace them with the mean, median, or mode of the feature. /backward fill is useful for time series data. Use neighboring values to fill in gaps. Dropping rows or columns with a high percentage of missing values is another option, but should be done carefully to avoid losing important information. Feature transformation techniques are important pre-processing steps to prepare data for machine learning models. This slide provides a summary of 4 key feature transformation techniques: min-max scaling, normalization, standardization, and log transformation. Each technique has a specific purpose and is best suited for certain types of models and applications. Min-max scaling transforms features to a specific range, usually 0 to 1, which is useful for k-nearest neighbors and k-means clustering. Normalization adjusts values to a common scale while preserving the original data distribution, making it well-suited for neural networks and deep learning. Standardization centers the data around the mean with unit variance, which is beneficial for principal component analysis and support vector machines. Log transformation can reduce skewness in highly skewed distributions, improving the performance of linear regression models. This slide provides a summary of key feature transformation techniques used in machine learning. Encoding converts categorical variables to numerical format, which is useful for decision trees and random forests. One-hot encoding creates binary columns for each unique category, which is helpful for linear regression and neural networks. Dummy encoding is similar to one-hot but removes one category to prevent multicollinearity, useful for regression models sensitive to this. Feature hashing maps high-dimensional categorical features to a fixed size space, which is valuable for natural language processing and large-scale text analysis. The purpose and best applications of each technique are outlined, providing a quick reference guide. Feature engineering is a crucial aspect of machine learning that requires continuous learning and experimentation. It's an art as much as a science, so staying up to date with the latest research and techniques is important. Applying these methods to diverse datasets will help you gain hands-on experience and develop a deeper intuition for feature engineering. Collaborating with data science communities can also provide valuable insights and learning opportunities from others' experiences. Remember, feature engineering is a fundamental skill that requires dedication and a willingness to explore and experiment.